Okay, let me give the second part of lecture 8. It is much shorter than the first part. So before this short break, I mentioned a network model, and of course this can be extended in many different ways. For once, I assumed that the underlying social network was static, so it was fixed. You might consider a time dynamic network, in particular if you look at long-term perspectives. Of course, also the underlying social network changes. You might want to have a network containing clustering, and maybe you have a time-varying transmission probability or dependence between if you infect one of your friends, you could have degree correlations. There are a lot of different extensions. This was more like an illustration. Anyway, here is an exercise which shows that not only the mean degree and the transmission probability, but also the variance is important in determining R0. So now a second sort of project where I have done some work some time ago. Now I will only go through this briefly, but this is, if you think of a sexually transmitted infection and you think of a heterosexual community, so maybe not HIV, but perhaps chlamydia or some other disease which is typically spread among heterosexuals. So then you might neglect homosexual contacts, and before we had the number of partners an individual has, and you had a transmission probability, but if you have a heterosexual community, you have to consider two different things. So the females have a certain degree distribution and the males have possibly another degree distribution. And then there is a transmission probability. Maybe I should have had used different symbols. Maybe it should say probability F to M and M to F. So let PF symbolize the probability that an infected female transmits to a susceptible male. And PM is the opposite probability, so it's a probability that an infectious male transmits to a susceptible female friend or partner. Of course, it must hold that if there are equally many males and females, it must hold that the mean of this degree distribution must equal the mean of that degree distribution, but the full distributions need not be equal. But there is some type of relation connecting the two. How would you model such a graph? Well, the simplest one, if you neglect other types of clustering and things, is that you make a list of all the females and you make another list of all the males, and then you draw stubs going out of this by drawing copies from this distribution. So the first one happened to get degree 1, the second one degree 2, the third one degree 2, the fourth one degree 0, and so on. And then on the other list of males, you draw the degrees from this degree distribution. But now it looks slightly different. So for instance, here there's one individual that has degree 4 and many more individuals have degree 0. So it seems like the two degree distributions are different in this illustration. So this reflects your underlying social network. And then if you start, and then you connect, you connect completely at random. So if you have 2 stubs here, 1 stub here, 2 stubs here, and 4 stubs here, and you have 1 stub, 2 stub, 2 stub, 2 stubs, 2 stubs, you connect these stubs completely at random. And then your model says that if this individual is infected, she infects that male with probability PF. And if this individual gets infected, this male gets infected, he infects that female with probability PM and that female independently with probability PM. And then it goes on like this. This is called a bipartite graph, by the way. So then the question is, what happens with such a model? Well, you can actually compute what is R0. It looks very complicated, but on the other hand, it's very similar to the previous illustration. It's just that it's a product of two things, and we have taken square root in front of both things, and what is within the square root is the same as what was in the previous example. So as before, a heavy-tailed degree distributions makes R0 large. If this is large and if that is large, it makes R0 large. So promiscuous people play an important role. However, in the model, it was assumed that there is a fixed probability of transmission between each partnership. But in reality, probably most likely the probability of transmission depends on how many intercourses there are in such a relationship. And it also seems quite likely that individuals with many partners will tend to have fewer intercourses per partnership. If you just have one partnership for a year, maybe you have many sex acts, whereas if you change partner each week or each month, then the overall number of sex acts per partnership is typically smaller, and this should reduce R0 compared to the model that was shown on the previous slide. The expression for R0 was shown on the previous slide. And this is something we investigated together. This was together with two sociologists. And what we did is we assumed that individuals have short and long-term partnerships. So we divided partnerships into short and long-term partnerships. And then there were two types of edges, you can think of it, maybe a thick and a thin type of edge. And for that, you can compute a new reproduction number. And what is the effect of this will depend on what fractions are of the different types, of course. But then we tried to fit this to data, and the data was from an anonymous study of sexual habits in the community in Gotland, young people. And what was asked was, how many sex partners during the last year did you have, and how many sex acts in each relationship? So that gives some type of information about it. And what we did was, we said that what is the probability of transmission for short and long term? That was estimated in the following way, that we assumed that there was a per sex act transmission probability, and then the probability of transmission is 1 minus p raised to the power. So each intercourse you have probability p to transmit. The only way not to get infected is that you avoid infection each of the sex acts that you have. And then we categorized relationships into either long-term and short-term relationships. And for that, we fitted data and fitted to data. But then the question was, how do you distinguish between short and long-term relationship? We looked at a few different things, but let's consider the following, where the box is where one sex act is the short-term relationship, and anything more than one sex act is a long-term relationship. We compared that to the situation where we did not distinguish between different types of relationships. And then we plotted R0 as a function of this transmission probability, which we assumed was symmetric. So PMF we assumed was equal to PFM. And then we see that for realistic values of this PMF, we see that this was the expression without taking long and short-term relationships into account. And if we do take them into account, we see that R0 is actually reduced as we believed. So heavy tail degree distribution still increase R0, but acknowledging short and long-term relationship reduces this effect to some extent. So let me end by making an important statement, which I already alluded at earlier, and that is that if you have a heterogeneous model, typically R0 becomes bigger, but the final fraction getting affected need not become bigger. So let me illustrate this with an academic example, not claiming to be any realistic at all, but consider two types of networks. Both networks have the same mean degree 4. In network 1, all individuals have degree 4, so there is no variance at all in the degree distribution. And this expression here, which is contained in the expression for R0 equals 3. And then consider another network, not claiming to be realistic, but anyway, suppose that half of the community have 1 friend and half of the community have 7 friends. So the mean of that is also 4. And what is the standard deviation? Well, the mean is 4, and everyone has a deviation which is either 3 below the mean or 3 above the mean. So the standard deviation is 3, and the variance is hence 9. So then this expression, which is part of the basic reproduction number, equals 5.25. And now we consider two different diseases. One has transmission probability 0.25. For network 1, this implies that R0 is equal to 0.75, because here we have 0.25 and this thing had the value 3. So R0 is 3 divided by 4, which is 0.75, whereas for network 2, R0 is equal to 1.31. So we see that for disease 1, R0 is larger for network 2, and an outbreak is not possible in network 1 since R0 is below 1, whereas it is possible in network 2. So clearly for disease 1, network 2 is more problematic than network 1. But now we go to another disease which has higher transmission probability. So suppose disease 2 has higher transmission probability equal to 0.75. Then for that disease, network 1 has R0 equal to 2.25, and network 2 has R0 equal to 3.93. So the conclusion for disease 2 is that R0 is larger for network 2, just as it was for disease 1. However, now an outbreak is possible in both networks. So the question is, which outbreak will have a bigger, which network would have a bigger outbreak? And the answer is that network 1 will actually have a bigger outbreak than network 2, because in network 2 there are many individuals that have degree 1, and they have a good chance of escaping infection. So if you remember from the previous slide, for disease 1, network 2 was the worst case and network 1 was better, whereas for disease 2, network 1 is the worst situation. So the general conclusion, which holds for a wide range of different type of heterogeneities. So if you think of starting in a more homogeneous situation and then heterogenizing in some way, nearly always this has the effect that you increase R0. So if the original model could be homogeneous, but it could also be heterogeneous, but where you have added one more heterogeneity. If the original R0 was small, then an outbreak will become bigger if you heterogenize. However, if the original R0 is large, then heterogenizing may very well make the outbreak smaller. So by making things more heterogeneous, you always increase R, but you don't always increase the outbreak size. So that ends this lecture 8, and I will meet you on the live session on August 4.